Hey everybody, it's Thursday, February 4th, and as you can see here in the aim today, our goal for today's video is vague. Now, the point for today's video here, at least to start us off, is to review the experiment from yesterday. I want to go over the calculations, I want to talk about the measurements, I want to get into those analysis questions a little bit, and obviously since I'm still making this video, I don't know how long it's going to be. Perhaps there will be a little introduction to momentum at the end. We'll see how long this beginning part takes us. So yesterday I gave you a video lab where I asked you to do an experiment. And in part A of the calculations section, which was really where I left you to finish the lab on your own, there was a little data table for measurements. And so I want to go over those measurements here and then talk about how we can use those measurements to do the calculations. So in the last part of yesterday's video, I told you in any actual application, it really makes a lot of sense to call the zero height the lowest point reached by the objects in the system. And since the system here includes the cart, and that's really the only thing that's moving, it makes sense to consider the lowest point reached by the cart the zero height. And so notice here, that would be 1, 2, 3, 4 lines below the little line that peeks out here underneath the ramp. And so that should be the height to which all measurements that you're making in this lab are referenced. And so the first thing you had to do, as you saw in the data table, is you had to measure the initial height of this cart. And so notice here we have the same reference line drawn. This is 1, 2, 3, 4 lines below that line that just peeks out underneath the ramp. And so that's the measurement we need. And as you can see here, this object is located with its center of mass at an initial height at the top line. And so all we need to do is count the number of lines here above 0. We have 1, 2, 3, 4, 5, 6 horizontal lines above the 0. Now, as you can see here, it says the horizontal line spacing is 1 centimeter, and so that means this line would be 6.0 centimeters. That's almost impossible to read, so 6.0 centimeters, or 0.06 meters. Of course, converting these things to meters is not totally important for right now, but when we do the calculations, we're going to want all of these measurements in meters, so the units work out appropriately. So our initial height here is 6 centimeters. The next part in the data table asks you to measure the minimum height. And of course, the smart thing about making the lowest point reached by the cart our 0 line is that now we can just say the minimum height is 0. And so the minimum height here is what we're just going to call 0 centimeters. And the next part in the data table asks you to find the final height maximum, or in other words, the height that's reached by this cart as it rebounds back up toward the top of the ramp. And so as you can see here, we don't have to go too nuts about this because notice this is just 1 line lower, so we should already know what the value should be. But notice once again, we have our 0 line drawn at the same location, and so that should be 1, 2, 3, 4, 5 centimeters above the 0 line. And so we're going to call that final height 5 centimeters. And so now here we have the initial parts of our data table completely filled out. I actually have that in here on a later slide. So let's just go ahead and fill those things in now. The initial height is 6 centimeters, which we can call 0.06 meters. The minimum height is 0 centimeters, or 0 meters. And we have our final height maximum is 5.0 centimeters, which we can call 0.05 meters. And now we are able to move on to the spring length part of the measurement. Now, I think hopefully the data table here, whatever you want to call it, made it clear to you. But it's really important, obviously, for this step to remember that the x that is used in the spring force equation and the elastic potential energy equation is the stretch length or compression distance, whatever you want to call it, from the equilibrium position. And so that's why we have to measure both the length of the spring before it's compressed and the length of the spring after it's compressed, because the difference between those two numbers is the number that we're actually going to need to use in our equations. And so if you look at the initial spring length, again, this is a judgment call. I don't really think there was any judgment in the height measurements because it was pretty obvious with the marking on the center of mass of the card and the way they set up the lines that it was exactly at 6 at the initial height and exactly at 5 on the final height. Having said that, here there is some room for judgment. And so I think here, if you're looking at the middle of this last little rung of the spring here, the way I see it, and again, there is room for disagreement because there is uncertainty in any measurement. The way that I see it is this is pretty much directly between these two lines. Now, of course, it's really important to realize here that if this line is 6 and this line is 8, then that means this line is 9 and this line is 7. And since there are only 4 tick marks in between these lines, that means that's going to be 8.2, 8.4, 8.6, 8.8, and then 9. And so the way that I see it is that this thing is exactly between 8.4 and 8.6. And so I'm going to call that 8.50. Again, we know for sure it's in between 8.4 and 8.6. And so I can go ahead and estimate that next digit. And you could call it 8.49 or 8.51. I think it makes just sense to me. I think it looks like it's exactly halfway between them. So I'm going to go ahead and call that 8.50. And of course, notice the unit here is centimeters. So I'm going to go ahead and write that down as 8.50 centimeters. And I can convert that to meters, but I'm not even going to bother at this point because I got to subtract these two numbers anyway. And this is really the only number that I care about. And so I'll just convert that to meters at the end of this. Now, once again, for the final spring length, there's some arguments that can be made. I think that makes pretty good sense. Looking at where the middle of this part of the spring is, it is for sure between the 4.2 and 4.4 line. But to me, and again, can be some disagreement about this because there's uncertainty in any measurement. To me, it doesn't look like it's halfway between. To me, it looks closer to 4.2 than it does to 4.4. So I'm going to go ahead, and obviously there's no way of knowing this because this is just an estimation, but I'm going to go ahead and call that 4.25 centimeters. Again, if you're anywhere in the ballpark here, that's totally fine. But that is the way that I see it. And so we've got an uncompressed spring length of 8.5 and a compressed spring length of 4.25. Now, our x, which is the distance from the equilibrium position, is just going to be the difference between these two values, where the uncompressed spring length we can call x final, and the compressed spring length we can call x naught. And notice here it actually works out quite simply because 8.5 is exactly twice 4.25, so the subtraction here works out quite simply. You have 8.5 centimeters minus 4.25 centimeters, and of course, you get 4.25 centimeters for your x if those are the numbers you used. Of course, whatever numbers you used are totally valid, at least if you did the measurement remotely correctly, because there's uncertainty in any measurement. And this is the number that I'm going to convert to meters by moving the decimal point 2 places to the left. And so that gives me, in meters for my x, 0.0425. And I'll just go ahead and write x equals, and that's that. That is more or less what your data for this experiment should look like. Now, you already submitted this sheet yesterday, so hopefully you had things down that were remotely similar, or at least, close enough. But the point here is now I am going to show the calculations that you should have performed with this data. I am going to go out on a limb here and assume that all of us did not do this exactly the same. There are probably some subtle differences in the measurements we made. I'm going to guess that our heights are probably the same. Maybe you missed the memo about calling the minimum height 0, and so you might have 11 centimeters for your initial height and 10 centimeters for your final height maximum. But again, all that matters are the changes. And so, if you recognize that the overall change in height was just 1 centimeter, then that's fine. And either way, on the way down the ramp, the thing did experience a change in height of 6 centimeters, then we should get similar answers. The reason why I'm bringing this up, of course, is because I just want to drive the point home that it's possible that you have an answer that's slightly different than mine for this part. And if you do, that is perfectly acceptable. Let's get into the calculations. Part B of the calculations section said calculate how much work is done by friction, W with the subscript F, on the cart during the trip down and back up the ramp. Now, if you recall, I'm not going to go through the whole thing again here, but if you recall in yesterday's video, we went over the equation for this part, and we said the equation based on the trip down and back up the ramp, the whole thing should be the initial gravitational potential energy equals the final gravitational potential energy plus the work due to friction. I now realize that I am looking at this, that I accidentally wrote an S there, but that should be a G. So the initial gravitational potential equals the final gravitational potential plus the work done by friction over this interval. Now, again, we mentioned the part yesterday that work due to friction in a conservation of energy equation is a little sketchy. But since we already wrote the heat here, we can get away with that. I'm not going to show the whole thing again because now we're just trying to calculate it. But that's the point. We can now use this equation, now that we have our measurements, to calculate the work done by friction over the whole situation here, from the initial state being at the very top of the ramp and the final state being back up at its maximum height, which ended up being 1 centimeter lower. And so here, what we're going to need is we're going to need our initial height, which we called 0.06 meters, our final height, which we called 0.05 meters. I think I might have just said centimeters there, but we already converted it to meters, and so that's the number we need. We have our G, which is 9.8 meters per second squared. Our mass, which hopefully you realized in the video, was labeled as 257 grams. So that means that's 0.257 kilograms. And we are looking for the work done to friction over the whole interval, which we called WF2. And so our equation here was the initial gravitational potential energy equals the final gravitational potential energy plus that work due to friction. And so we have here the work done by friction is equal to the initial gravitational potential minus the final gravitational potential energy. And when we sub in the equations for those values, the initial and final gravitational potential energies, we get mg delta y1 minus mg delta y2. Now notice the structure of this equation is such that the work due to friction is going to come out positive here. We know, according to our normal sign convention, that it should be negative. It's only coming out positive here because we really subbed in the absolute value for the work due to friction into the conservation of energy equation with the heat that we originally started with. We're not going to go nuts about the distinction for now. You should recognize, and it shouldn't be that confusing, the work done by friction here technically should have a negative sign because it represents energy that is taken away from the system. That said, here we're just trying to calculate the magnitude or the absolute value, the size, however you want to refer to it, and so we're not going to go nuts about it. I think to make my life easier here, noticing that both of these terms have an mg, I'm going to go ahead and factor that out. And so notice here, I just take mg times the change in heights, and that's going to give me my work done by friction. Pretty simple here. So this, notice, represents the difference in the overall energy, and that should make sense. The work done is equal to the change in energy. And so I'm going to plug in my mass here, which is 0.257 kilograms. G, 9.8 meters per second squared. And then I've got to multiply that by those difference in height. So I have 0.06 meters minus 0.05 meters. Notice that difference is going to be equal to just 0.01 meter. And when I multiply 0.01 times 9.8 and then times 0.257, I end up with the work due to friction for this part equal to 0.0252 joules. Now, we're not going to go too nuts about this here. I'm going to refer to all of these numbers to 3 significant digits because the mass was given to 3 significant digits and my spring measurements were given to 3 significant digits. Clearly, it should be recognized that my heights are not used to 3 significant digits here. We can go ahead and assume that those are exact measurements. The reason why, of course, is because that was overlaid on the video and they perfectly lined up with those with that center of mass marking on the cart. And so we're not going to go too nuts thinking about this in too crazy terms. I just want to be clear, though, this number I'm arriving at 0.0252 because the number that you actually should get out of the calculator when you do this measurement is 0.25186 joules. And so we say that that's approximately equal to 3 sig figs to sorry, there should be another 0 there, 0.0252. That 8 causes that 1 to round up to 2. And that's it for the work due to friction calculation over the whole trip. Over the whole trip, as you can see here, this system lost a pretty tiny amount of energy. And that should make sense. First of all, its initial height was only 6 centimeters above the final height, and so it didn't actually have that much energy to begin with. But also, it should be noted that this thing is rolling, and it is like a lab cart, which are traditionally designed to be pretty low friction. And so there's not a whole lot of energy lost in the system. It only got back up to a height that was 1 centimeter below where it started. So we wouldn't expect this number to be particularly large. And that's it for this first calculation. Now, hopefully you got this one right, but if you didn't and you made a mistake or you forgot to convert the distances to meters or whatever, you may want to take a second to pause this video here and write that down. And when you hit play, we'll take a look at part C, where we calculate the spring constant. Moving on to part C requires us to do a little more work. It's asking us to calculate the spring constant for this spring based on your data and your equations. The first thing that we have to recognize is the way we calculate the spring constant involves the conservation of energy equation only for the trip down the ramp. And that means that the work due to friction that we just calculated is not going to be the number that we're going to use for the work due to friction here. The assumption we made, if you remember, for this part, was that the work due to friction on the trip down was equal to the work due to friction on the way up. And so that means the work due to friction just on the way down is going to be half the work due to friction that we just calculated, because the work due to friction that we just calculated is for the whole trip. So if it's equal on the way up and the way down, then that means each part is half of the total, right? And so here we're going to just take half of the number that we just previously calculated. And when you do that, notice the number that we had here was 0.0252 joules. And so when we take 0.0252 and we divide it by 2, we end up with 0.0126 joules. And that number is what we're going to need to use here in our list of knowns. So we can go ahead and write that down. We have the work done by friction over this first segment here. Just the trip down the ramp is 0.0126 joules. Of course, we're going to need our mass here. That's 0.257 kilograms. We have our G, of course, is 9.8 meters per second squared. We know that the height that this thing started at was 0.06 meters. And we're looking for the spring constant. Now, the part of the video from yesterday that I also left out, because I wanted you to do it, was to write an equation for the spring constant. Notice I basically set you up here, though, to be able to do that, because the equation was the initial potential equals the final spring energy plus this work due to friction here, WF1. And so we'll go through that part at least a little bit because that wasn't reviewed in the video yesterday. And then hopefully you'll be able to see how this all works the way it does. And so the equation that we developed from that part was that the initial gravitational potential energy is equal to the final spring energy plus WF1. And so that means if we solve this for the spring energy, we get the initial gravitational potential energy minus the work done by friction, number one. And here now we have to sub in the equations. And so we get 1/2 kx squared equals mg delta y1 minus the magnitude here of this work done by friction. And so notice what I need to do to solve this for the spring constant is I need to multiply both sides by 2, so that whole thing over here on the right-hand side by 2, and then divide by x squared. And when I do that here, I'm going to get 2 times this whole thing, mg delta y1 minus wf1, and then all of that is going to be over x squared. And so plugging in here, I have 2 times this whole thing, 0.257 kilograms, times g, 9.8 meters per second squared, times that initial height of 6 centimeters, 0.06 meters. I am then going to subtract from that the work due to friction on just the way down, which is 0.0126 joules. Close up that numerator, and then all of that is over x squared. X here, I didn't write down in my list of knowns. X here, remember we solved for as 0.0425 meters. And so we'll divide that by 0.0425 meters and make sure we square it. And when you do that math, plugging in all those numbers here, you should end up with a spring constant, according to the calculator, of 153.37 newtons per meter, or to 3 sig figs, 153 newtons per meter. And that is it for the calculation of the spring constant. Now, I'm going to go ahead and say, based on the differences in the measurements, if you have a spring constant that's like anywhere between 140 and 160, maybe 165, depending on exactly what you wrote down for the measurements, it doesn't mean your work is wrong. It means your work is right. We just used different measurements, so we got a slightly different result. There's some uncertainty in the measurements. But your answer here should be somewhere in the ballpark of about 150 newtons per meter. And that's it for the spring constant. And so basically that's it for all the calculations. There were, at the end of this video, just 2 analysis questions for you to consider as we're wrapping up this experiment. The first question said, is mechanical energy conserved as the cart rebounds? How can you tell? Now, whether you realized it or not, this was actually the first question that I asked you in yesterday's video. In yesterday's video, I asked you, is there friction in this system? And yeah, there's friction in this system. So no, the mechanical energy is not conserved in this system. That should be a period. Mechanical energy is only conserved in the absence of external forces. And I'll write here in parentheses, work. And so since the cart doesn't rebound to its initial height, which was 6 centimeters here above its lowest point, we know that some of the mechanical energy initially present in the system is lost due to friction. Friction, a non-conservative force, acts to convert mechanical energy to heat. This is a really good way of telling whether something loses energy or not. You bounce it. If it gets back up to the same height, there's no energy lost. If it doesn't, then there was energy lost. And that's the idea. This is really going to come into play when we get into the next unit, because the next unit is all about objects colliding with one another, momentum. And so we can see if the object gets back up to its same height, that momentum and energy were conserved. If it does, and if it doesn't, then energy is not conserved. Take a second to pause this video here and add any parts of this that may be missing to your explanation. And when you hit play, we'll move on to the second question. Okay, the last analysis question on this sheet, part B, said, what is the problem with the assumption that the work due to friction down the incline is half of the work due to friction from the initial height to the highest point on the trip? Whether or not you went through this whole lab realizing there was a problem with that assumption, there's a problem with that assumption. It's actually fairly straightforward, but it's pretty easy to overlook, I think, especially when your teacher is just telling you, assume the work done by friction on the way down is half the work done by friction on the way up. So there are a number of things that you can say here, but I think the most obvious reason why this assumption is wrong is figured out by looking at the equation for the work done by friction. Work done by friction is equal to the force of friction times the distance. And the whole point of this problem is that the object does not make it back up to the same height. So the idea here is that because the work done by friction is directly proportional to the distance traveled by the object, the fact that the cart doesn't rebound back to its original height means that the distance traveled by the cart is not the same on the way up as it is on the way down. On the way back up, it's actually traveling slightly less distance. Now, we could calculate it if we knew the angle for the ramp, right? Because the length of the ramp then would be like the hypotenuse of the triangle, because we know the heights, the adjacent, or I guess that would be the opposite side from the angle. And so the basic idea here is that the work done by friction on the way down is actually a little more than half of the total work done by friction, because the distances are not equal. It goes 6 centimeter height worth of distance on the way down, if you follow that weird phrasing. And then it only comes 5 centimeters of height worth of distance on the way back up. And so that leads to a little bit of complication. Now, this next part you were not actually asked to consider at all in this question, but I do think it is an important intellectual exercise to consider this sort of thing. When we do an experiment, generally we make assumptions about how things work. We assume that something is frictionless when it might not be. We assume that air resistance doesn't really matter when that might not be true. And so I think it is important to just take a moment to consider how that assumption being wrong affects our measurement of the spring constant, which was the whole point of this experiment. And if you go back to the calculation here, you'll notice that in order to calculate the spring constant, we took the potential energy that this thing had in the beginning, which is not affected by this assumption. We divided by the square of the compression distance, which is not affected by the work done by friction, but we subtracted the work done by friction on the way down the ramp. Now, it should be noted, this calculation is not corrupted by that assumption, because this is for the whole trip. This calculation, on the other hand, is. Because we took the result of our previous calculation, 0.0252 joules, and we cut it in half. We shouldn't have cut it in half. Maybe instead of being 50% of the work done by friction on the way down, it's more like 55%. And that really is the point for this second thing I wrote here, is that this means that our measured spring constant is actually most likely too large, because we should have subtracted a larger number from the mg delta y in the numerator of the equation for the spring constant. If we subtracted the bigger number, say instead of dividing the work done by friction over the whole trip by 2, taking 50% of it, let's say we took 55% of it, the number that we would have gotten for the work done by friction on the way down the ramp would have been a little bigger. We would have subtracted a number then from the mg delta y that would have been a little bigger, and that would have made the spring constant a little smaller. So our measured calculation, however you want to put it, for the spring constant is actually probably bigger than it actually is. Again, it's probably not bigger than the spring constant actually is by much, but it's probably a little too big. And that's really all that needs to be said for the analysis for the error for this experiment. If you missed any part of this explanation in your worksheet, you can pause this video here and write that down. And when you hit play, we'll wrap it up for today. All right, everybody, that is it for today. Now, like I mentioned at the top here, I really wanted to introduce momentum here in this video because we're basically already at the half-hour mark for this video, and tomorrow is a test. We'll just go ahead and leave it there for today. Tomorrow, Friday, is your test on gravity and uniform circular motion, and that means we will begin momentum, impulse, and conservation of momentum on Monday. Good luck on the test. If you're coming to the Zooms, I'll see you in tomorrow's Zoom meeting. And that's it. Take care, everyone.